Loss functions in machine learning for AWS AI specialty exam. Loss functions quantify the error between a model's predictions and the true values, guiding the learning process. Choosing the right loss function is critical and depends on several factors: the type of learning, supervised, unsupervised, semi-supervised, the nature of the target variable, continuous or categorical, and the specific characteristics of the data, e.g., presence of outliers, class imbalance. Supervised learning uses labeled data, input-output pairs. Regression, continuous targets, the goal is to predict a continuous value. Mean squared error, MSE, average squared difference between predictions and actuals. Simple and widely used but highly sensitive to outliers due to the squaring operation. Mean absolute error, MAE, average absolute difference. More robust to outliers than MSE as it doesn't amplify large errors as much. Huber loss, a combination of MSE and MAE, acting as MSE for small errors and MAE for large errors. Offers a balance between robustness and differentiability. Root mean squared error, RMSE, the square root of MSE. Useful for interpretability as it's in the same units as the target variable. Log-Kosh loss, a smooth approximation of Huber loss, twice differentiable everywhere, which can be beneficial for some optimization algorithms. Classification, categorical targets, the goal is to predict a class label. Binary cross-entropy, log loss, measures the difference between predicted and true probability distributions for binary classification. Standard for logistic regression and binary neural network outputs. Categorical cross-entropy, extends binary cross-entropy to multi-class classification, mutually exclusive classes. Used with softmax output layers in neural networks. Sparse categorical cross-entropy, functionally equivalent to categorical cross-entropy but uses integer class labels instead of one-hot encoded vectors. More memory efficient when the number of classes is large. Hinge loss, primarily used with support vector machines, SVMs. Focuses on maximizing the margin between classes. Sensitive to outliers. Squared hinge loss, a smoother version of hinge loss, making optimization easier. Focal loss, addresses class imbalance by down-weighting the contribution of easily classified examples, allowing the model to focus on hard-to-classify examples. This is particularly useful when one class is significantly more prevalent than others. Unsupervised learning, uses in labeled data. The loss here is an objective function that guides the discovery of data structure. Clustering, k-means, minimizes the sum of squared distances between data points and their assigned cluster centroids, intra-cluster variance. DBSCAN, identifies clusters based on density. No explicit loss function is minimized directly, but parameters like epsilon, radius, and minimum points influence cluster formation. Hierarchical clustering, builds a hierarchy of clusters using linkage criteria, e.g., single, complete, average linkage, to measure cluster similarity. Dimensionality reduction, principal component analysis, PCA, maximizes the variance explained by the lower dimensional representation. The objective is to find principal components that capture the most significant directions of variance in the data. TSNE, preserves local neighborhood structure for visualization in lower dimensions. It minimizes the divergence between probability distributions in the high-dimensional and low-dimensional spaces. Anomaly detection, one-class SVM, maximizes the margin around the normal data points in a high-dimensional space, effectively identifying outliers that fall outside this margin. Isolation forest, isolates anomalies by randomly partitioning the data. Anomalies are expected to be isolated with fewer partitions. Semi-supervised learning, uses both labeled and unlabeled data. Combines supervised and unsupervised loss components. A supervised loss, appropriate for the labeled data's task, regression or classification, is combined with a regularization term or a consistency loss. The consistency loss encourages similar predictions for similar data points, whether labeled or unlabeled. This helps the model leverage the information in the unlabeled data. Loss functions and AWS services. SageMaker built-in algorithms employ predefined loss functions, often configurable through hyperparameters. Custom loss functions require custom training scripts. SageMaker framework estimators offer full flexibility to define custom loss functions using the framework's APIs within the training script. Amazon Forecast uses algorithm-specific loss functions optimized for forecasting, e.g., quantile loss for CNNQR. Loss function selection is managed by the service.